Okay, thank you for being still here for last talk. So this last talk would be about decoding Meteor M2. So what I would like to emphasize is I assume that most people in this room don't care at all about Meteor M2. The topic here I would like to address is to use Meteor M2 as the reason for addressing all these fascinating topics. I should emphasize, I'm trained as a physicist. I've never been taught about any of these things here. So I discovered everything by myself. I found it very fascinating to be discovering all these signal processing techniques that you find in the various documentation about digital communication. And I want to show you how getting from the raw data, QPSK, all the way to a JPEG image, as you can see here, will be addressed in this talk. So our team did not care to give you a talk with 2 semesters of signal processing in 20 minutes. I do. So also I should emphasize, if you just want to get the image, you can go out of the room because this Meteor decoder is doing a much better job at what I'm going to show you. This is working very well. I want to go step by step into what is going here. So really for me, the topic is understanding all these things, not using a readily available software. So that's the topic of my talk. So I'm lucky enough to be going twice every year in Arctic regions for glacier monitoring. And so I'm lucky enough to be following all these polar orbiting satellites, so low Earth polar orbiting weather satellites, including amongst the various LEO satellites, the one from the Russian Meteor. So why are Arctic regions most favorable for this kind of monitoring? When you have solar synchronous satellites, they will be in the polar orbit, 98 degree. So 90 degree would be right over the North Pole. And one of these polar orbiting satellites, here I've plotted the trajectory over one day. You see that when you're in Western Europe, here it's Besançon in France, the green circle is the place you would be if you wanted to see the satellite horizon. This is at an altitude of elevation of 15 degrees. This is at elevation of 60 degrees, below which I don't even bother to take my antenna out. In France, you will get at most 1 pass every day of one of these polar orbiting satellites. While when you go to an Arctic region, well, you've got all these passes. So it's fascinating because when you're learning to decode a new satellite, here you have like 10, 12 passes per day, while here you have 1 at best. So I'm investigating Meteor M2 in this context and also using the little RTL SDR receivers because, of course, when you go there, you're not supposed to take a big bag with full of hardware that's not related to your research. So here I can just put one of these little receivers at the bottom of my backpack, just find any 2 wires to make a dipole antenna once you arrive there, and you have your setup for receiving Meteor M2. So I'm sure many of you here in the room have already listened to NOAA. So the NOAA satellites are a dying breed because NOAA is no longer renewing their constellation of analog satellites. They started in the 70s. Now they are at NOAA 19. I think it will go up to 21, and then they'll stop the NOAA. So now we have to think about the future. And the future is digital communication. So digital communication is what is provided by CCSDS. So because the last speaker could not say, it is the Consultative Committee for Space Data Systems. And this is basically a body trying to standardize this communication. So that's a bit of a layout of what I want to talk. So when Bastian was showing you, I have my JPEG picture, then I have TCP/IP, then I have TCP, then I have IP. You've got all your OSI layers. And of course, when you want to decode a JPEG image on Firefox, well, you've got all these libraries for you. And for me, the exploration here was I collect this QPSK data at the output of GNU Radio running the RTL SDR data stream. And then how do you go from this QPSK all the way to the JPEG image? So for me, it's a little bit like if you were trying to listen to a JPEG image being transmitted in HTML with just an oscilloscope connected to your Ethernet cables. And for me, it's an adventure to try to get all the layers one after the other. So of course, in this talk, I don't claim to be going in detail. I would like to show you the outline. The slides will be available on the website, and I hope it will make you curious about getting into all this story. Now, you might be wondering, people have been working happily with NOAA, so why even bother with such a complex networking? So this is a talk I saw when I was at Huntsville at the Marshall Space Center from Dave Israel at the YZ conference, where he was showing you've got the International Space Station. The International Space Station is flying at 400 kilometer altitude and is visible, if you remember my little circles, on a radius of 1,500 kilometers. So this means you would need to put one station every 1,500 kilometers along the path. So this is what the Americans did for Gemini and Mercury. They had one ship or one station every 1,500 kilometers, but that's no problem because they only did 1 or 2 orbits. So you just needed to put a few stations along the orbit. ISS is rotating all over the Earth. Of course, you cannot put one station every 1,500 kilometers all over the Earth. So what is happening now is ISS is completely automated. The astronauts are running their experiments, but everything on the ISS is automated from ground stations. And the ISS is only visible from a radius of 1,500 kilometers. So the ISS is not directly talking to the Earth, but it's talking through the tracking and data relay system, the TDRS satellites, the geostationary satellites. So ISS, 400 kilometers, rotating quite quickly, talks to TDRS. TDRS are talking with each other, and TDRS is sending signal back to the Earth. Same is true for Hubble. Hubble Space Telescope is very expensive. You don't want to just run it as it is flying over your head. You want to continuously monitor Hubble Space Telescope measurements. And of course, you don't think that the US Air Force cares much about the science in Hubble Space Telescope, but once you figure out that Hubble is just a spy satellite upside down, you might figure out why you have TDRS here in the space. So, of course, here you have multiple satellites with multiple experiments. So you need a way of packetizing your data. You need to say it's satellite number X, which is sending data from instrument number Y. And how do you do this? Well, that's where you go from QPSK, which would be your Ethernet cable, all the way to the JPEG image through all the layers of OSI layer. OK, let's try to have fun with the OSI layers. So first of all, we need to predict where Meteor is flying. I still use SATRAC, despite the Y2K bug, which is still a patch and is not inserted. You can use WX to IMG. In the paper, I explained to you how you can cheat WX to IMG, which is no longer maintained, into thinking that one of the NOAA satellites is actually Meteor M2, and so that you can, so Meteor M2 is actually one of the NOAA satellites, so you can use WX to IMG, and if you have internet access, you can use the Heavens Above website. Again, the beautiful thing about being in Spitsbergen, Arctic region, 79° north, is you've got all these passes at high elevations, which of course you don't get in the Western in a Western European country, lower latitude country, you'll get 1-2 passes at best. Okay, so we know when Meteor M2 is flying. So we take our RTL-SDR, we collect the data. This is all stolen from the AirSpy website for receiving Meteor M2. Rational resampler, you have your clocking, so your Costas loop, which locks on the frequency offset between the carrier and the local oscillator, bit recovery, and so data clock recovery. And at the end, you got your soft bits. So already I needed to learn a first word when I was doing this. I didn't know what a soft bit is. So soft bit is IQ coefficients where your 1 and 0 are not yet saturated, but are still represented here by an 8-bit value, and you still need to identify whether it is most probably a 1 or a 0. So I didn't know what soft bit meant. So the first question is, are my data even worth investigating? So this is a spectrum. Unlike GPS, now we have strong signals, so you see there is something happening here. Is it a QPSK signal? Well, if we expand what Paul Boven taught us about GPS, where BPSK is collapsed here by squaring the signal, well, of course, if you take the nth power of an NPSK signal, you collapse, again, the spectrum spreading due to the PSK modulation. So here we take our raw signal. Well, there is something, but we don't know if it's the right modulation. We square it. It is not BPSK, so we haven't collapsed the spectrum. We raised to the 4th power, it is QPSK because your spectrum spreading has collapsed in the carrier. So we can get signals that are worth investigating further. It seems to be QPSK modulation. So once we've done this, we know it's a packetized system. Packetized system means something will be repeated. If we look at the documentation, you will find that all CCSDS compliant communication start with a header. Well, if you have packets, you need to know where the packet starts. And the packet start header is 1A CFF C1D. Try to remember this because I will keep on repeating this sentence all over the time. So at first, I don't know what this packet is. I just want to know whether there is some repeated header in the signal. So as shown in the previous speaker, you just autocorrelate the signal. If there is some redundancy, this redundancy will show. So by autocorrelating my signal, well, indeed, I see a peak at 16 kilobytes. I see a signal at 32 kilobytes. So there is some redundancy every 16,000 samples, I have some repetition. So it's definitely worth working further on this data. So the first thing that got me stuck, because again, I'm a physicist, I haven't been taught about digital communication, was convolutional encoding. So that's the topic of Martin's talk this morning. I'm just going a slightly bit further into it because I want to show you how it's decoded. I don't want to get into the encoding part. The encoding actually is very simple because they show you on various documentation as an XOR, so as was shown by Martin this morning. You just take your data stream and take convolution, so you try to mix all this data to create as much randomness as you can, so that if one of these bits is corrupted, you have a lot of chance, because you've spread the information over a long duration, to recover this information. So here it's a 7-bit long shift register. You have taps from which you XOR, and you get twice as many bits on the output as you had on the input. So this shift here will clock up, down, and sometimes take the output with one polynomial and on the other. So if you do this, you can also express this as a matrix where time is evolving over the x-axis, and you jump first coefficient, second coefficient, first coefficients of first polynomial, first coefficient of second polynomial, second coefficients of first polynomial, and so on. So you have your polynomial which are interleaved, and you just shift time. So that's another way of implementing your your convolution encoding. And the last way of saying it is you can do this as a state machine. So you take the various states of your polynomial here, you input a new bit into your system, and by inputting a new bit in your system, your shift register changes. So if you had 0 and you inject a 0, you stay at 0. And your output, you run the XOR on all these 0, you get an 0 output. If you inject a 1, well, your 0 goes to the last 0 drops, the 1 comes here, and you run this for the XOR, you get 1, 1. So you can make this as a state machine. So once you've discovered the state machine expression, you can write this as the evolution between the various states. So previously I had given names, A, B, C, D, to my various states. And then you can draw the state machine. So A stays in A goes to B if you have a 1. Then, so these are the input bits. So if A is fed or 0, it stays at A. If A, when it is fed a 0, will output 0, 0. A, when it is fed a 0, where A, when it is fed a 1, will output 1, 1, and so on. So you can draw your state machine. So encoding is very efficient, very easy. It's just XOR. Now, the reason I wanted to show you this is if you take the same description that we had here, but now you take it to decode, that's a 30-second description of the Viterbi decoding algorithm. In 30 seconds, what you have here is, let's imagine I have received this bit stream. So this is what I have received. So I split what I have received into 0, 0, 0, 0, 0, 0, and so on. And what you see here, I start with 0, 0. OK, I get 0, 0. That is most probably state A with a 0 output. 0, 0, state A, 0, 0. 0, 0, state A, 0, 0. So these 3 zeros are just A looping into the 0, 0. Now we get 1, 1. 1, 1 is a feasible output of state A that gets us into state B. So we go into state B. When we're in state B, we get 1, 1. But that's not possible. We cannot get a 1, 1 out of state B. We can get 1, 0, 0, 1. Well, at the moment, we don't know what's the best option. So let's follow the 2 possible paths. We know it's wrong, but let's follow the 2 possible paths. After that, we got 0, 1. So we could be here, C, but C cannot have 0, 1. It can be only 1, 1 or 0, 0. So C would create 2 errors. That's the wrong path. So we cut it out. And Viterbi tells you, let's not follow this one. No, we go into this path here because 0, 1 is a valid output of D that would be considered as a 0. And then you go on and you follow your path. So if I add the output bits, here you have the number in red of errors. 2 errors means we give up on this particular branch and we continue with the branch with only 1 error. And this unique error continues with a consistent path that tells you in the transmission this bit was erroneous. So you see that by spreading the information over a long duration, there we had just a burst of 1 bit error. That's the point of convolution encoding. It's just a noise on 1 bit. And this unique bit has been recovered by Viterbi decoding. And then indeed we recover 1A, which is the first byte of our synchronization word. So OK, we've understood Viterbi decoding. So now, well, we can go for So yeah, sorry. This is what so if you don't want to go into all the math by yourself, you have libfec with you, and by K9Q, and libfec will do the job for you. Here I put for you a very simplified chart of running libfec for Viterbi decoding. Just don't do the same mistake as I did. libfec will not take as input 0 or 1. You need to feed it 0 or 255. It's working on a byte. So I struggled for like a couple of weeks. Why is libfec not decoding? Just because I was giving it 0 and 1. Let's give it 0 and 255. And again, the word, encoded word here, will be decoded as 1ACFFC1D. So we know that the encoded word of Viterbi, you can use libfec to encode or to decode. So this is the encoded word, and this is the decoded word. This is how you do it with libfec. Okay, so we've got libfec. We can check that indeed we can decode our word. So if we have the sequence, so this is an example that was given to me by the author of GR Satellite, by Daniel Estevez. I hope I pronounced his name correctly. You've got the FEC decoder here, as was shown by Martin this morning. And if I feed my GR decoder here with the encoded word, indeed I can get the output, which is 1ACFFC1D, except sometimes I get wrong messages because you see here that my input stream is repeating. And if I repeat my input stream, the hypothesis of Viterbi is to start with a shift register that is full of 0. And that is not correct because here, after the first decoding, I don't have a shift register full of 0. So then I have one wrong sequence, and then I go back to 1ACFFC1D, which is the correct sequence. So you can play with this, and it's an opportunity to see how the header word of CCSDS is decoded by the FEC decoder in the radio. What is the sequence? Well, as we did for GPS, now I should be able to correlate my received signal with a synchronization word after encoding by Viterbi, and it miserably fails. You see absolutely no correlation peak. I cannot find in my QPSK signal the set of bits of my encoding word. Why is that? Well, I associated the usual constellation to my QPSK. QPSK is 4 phases, so I have 90, 180, 270, 360 degrees. And 270 degrees, and I associated a symbol, a set of bits, to each one of these symbols of these states. But why would I do that? Why would I not associate a different symbol to a different set of bits, pair of bits, to each symbol? So this is actually what you figure out when you read the source code of Meteor Decoder. You figure out that Meteor Decoder starts by creating rotated copies, all the possible rotated copies, which comes back to say, let's take the standard distribution of bit pairs of QPSK, and let's imagine, like in BPSK, you can have 0 or pi or 0, but in BPSK, it doesn't care because you just go to a 0, 1 or 1, 0, but you will still correlate, only you have an anti-correlation instead of having correlation. But for QPSK, you've got all these possible shift positions, so you can swap the real part, you can swap the imaginary part, or you can swap these parts here. And so if you look into Meteor Decoder, you indeed find that, well, I will not get with you, but you swap all the possible bit pairs. So 1, 1 becomes 0, 1, 1, 1 can become 0, 0, 1, 1 can become 1, 0. So you make all the possible combinations. And because you don't care about anti-correlation, these 8 possible bit swaps actually become 4 possible combinations because you have 4 ways of combining all these bits if you think that 1, 1 and 0, 0 are the same. So having done that, now you can see here all the possible correlations, and the only one that gives you correlation, I don't know if you can see this from the room, but you've got no correlation peak for all these cases, but here you've got these correlation peaks every 16,000 bits. So this means this is the right assignment of each symbol into the bit pair. So now I found how to convert my QPSK signal into the encoded Viterbi keyword, and by encoded Viterbi synchronization word, I can start decoding my sentences. So I will skip read Solomon, because actually read Solomon is a block encoder. So Viterbi is to eliminate random bits that have flipped during the communication. while read Solomon, or what, well, the reason I'm skipping it is because I investigated quite more deeply BCH, which is the encoder, block encoder in RDS that was investigated heavily by Bastian. So when I worked on BCH, I've put the reference here. You can look at how BCH is working, and read Solomon is just an extension of this. The only reason I'm mentioning this is you've got your data here. If you don't want block correction, which is someone is emitting and you've got whole blocks of data that have been corrupted, well, you can get rid of read Solomon. If you want to use it, just be aware, because again, you want to spread information over time because you want to recover as much information as possible. You will have interleaved read Solomon, meaning you have 4 interleaved read Solomon. You have data 1, data 2, data 3, data 4, data 1, data 2, data 3, data 4. You need to de-interleave, run the read Solomon decode recovery, and then re-interleave your data. So it's just, I will skip this because, because only I don't have time to get the details. And again, I give you the example how to run the read Solomon decoder in LibFEC. So if you want to give it a try by yourself, here is my data set. I voluntarily corrupt 4 bytes. I voluntarily corrupt bytes in the data set, so in the payload or in the correction code. And if I run this in my read Solomon decoder, indeed I detect, or LibFEC detects 4 corrupted bytes, and these 4 corrupted bytes are these values which can be recovered. So not only you discover which bytes are corrupted, but you can find the properly initial values of these bytes. So just demonstration, again, you have to run it by yourself. I can talk as much as I want. If you don't run it by yourself, you don't learn, so try it by yourself. Good, so we claim to have found out how to work with Viterbi decoder. We claim to have understood how read Solomon is working. So are the bits that we get out of a Viterbi decoder valid? That's, I can claim now I've done the job, I can go away. Well, we want a picture. We don't want a random set of bits. So the first thing we can do when we look at the data sheet is, or the documentation of a Meteor M2 transmission, whose I'll give you the references where you can find the documentation of the last slide. You see that there is telemetry data, and these telemetry data are encoded in a sentence to recognize, so that you know where your telemetry data are located. So you've got this magic sentence, 224, 168, 163, 146, blah, 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 191. So this magic sentence tells you, I am sending a telemetry frame. So what do? Well, we take all our decoded bits, and we cross-correlate our decoded bits with this sequence. And this is one of these all-inspiring moments where it works. You find this sentence in all your bits, and if you decode the following bytes, hours, minutes, seconds, you find that the information was collected at 11 o'clock, 48 minutes, 33 seconds, which is indeed the output of the Meteor decoder provided as a reference. So you see here that we have indeed properly decoded the Viterbi and read Solomon, or actually in this part I skip read Solomon, but we have understood Viterbi because we can find the telemetry sentence and we can decode proper information. Now, I found the telemetry, but still a bit far from pictures. But the next part, the end now is easy because I don't get the details. It took me a couple of months. This work has been started a bit more than a year ago. But once you've got the bits, it's just a matter of basically finding what the bytes are and checking whether they follow the standard. So I will not give the details, but indeed you see that you've got this header, which is always the same, that tells you, well, we're in a good job, there's an ID. Then they tell you have a counter. Well, indeed, these 3 bytes, you see that they're increasing one by one, so we're on the right path. And then they tell you, here is a header. So this is an address of the first payload, because the difficulty is that you've got the data packet and then you've got the payload packet, and there's no reason for the data packet to be synchronized on payload packets. So you might have payload lying over multiple data packets. So this is the address at which the first payload packet is starting, and so on and so on. So I will not give the details, but that's just a matter of following the protocol. So once you get the bytes, it's really easy. And finally, you are supposed on the payload to get JPEG images. And this is where I gave up. I said, OK, I'm not going to re-encode the whole Huffman encoder and everything. So this is where I just took this port of the decoder, the Meteor M2 decoder that was ported from Pascal to C++, and I just used their decoder. JPEG is standard bachelor level computer science signal processing training. I didn't want to write all of it again, maybe for the next training session. But yeah, I wanted to get some images, so I went. So to conclude the talk, that's what I get at first. So you are told in the standards, again, it's all detailed in the paper that I uploaded on the FOSDEM website. You are told that your frames, your JPEG images, are 8 by 8 bit frames. These 8 by 8 bit thumbnails repeat 14 times, and each one of these 14 times 8 bit sequences repeats 14 times along one picture line. And then you jump to a next instrument, because there are 3 wavelengths, which they call 3 instruments. You get one line of the next instrument, 8 bits wide, 1500 bit long, and then you go to the next instrument, and so on. So here you see that I had some missing frames, so some missing thumbnails that I had to introduce. So what I did here is, because you've got a counter, you know that when you have missing frames, here I just very stupidly did, if you're missing a frame, copy the previous frame. And this way I could fill the missing thumbnails. And here you start seeing some pattern. And here you've got one parameter in JPEG, which is called the coefficient, quality coefficient, which gives you the relation between the quantization and the quantization matrix. And here is no quality, so you see that the sharp pictures here don't have the same tone as the flatter area of the picture, but you start seeing here the Alps. And finally, by applying the quality coefficient, you get an image that is a bit more smooth, and that compares, I think, quite favorably to the reference picture that was decoded using the satellite, the Meteor decoder that you can find on the internet. So here you see Istria, you have Balaton Lake somewhere over here, I think. You've got Venice over here. So if you take the Meteor decoder, you get an image that is quite consistent with what we got by step-by-step decoding. So that was, of course, in 25, 27 minutes, a very fast highlight of the main steps. Go through the paper. The paper is actually about 50 pages long at the moment and increasing. But I'm trying to put every detail about the from IQ coefficient all the way to the JPEG image. CCSDS is a protocol for space communication. You might not care about weather satellites, but what Daniel Estevez is showing on his blog, and as mentioned by Paul, is this is the standard for most satellite communication, and that's going to be the future because no AA is going to stop the analog satellites. So I think if you're interested in satellite decoding, this is really worth investigating. Daniel Estevez is just addressing all the satellites, amateur satellites up there. Lucas Teske is a Brazilian guy who's working on GOET satellites, geosynchronous, and his website was very inspiring, despite at some point splitting the path of decoder. His beginning was very insightful. He helped me a lot by email. These 2 guys helped me a lot. This is the website that was hosting all the files about Meteor M2. Somehow, in between, in the middle of this investigation, it disappeared. I don't know where the site is. Hopefully, we've got a web archive. I don't know where this website is disappeared, but it's a fundamental repository of all the data, some of which cannot be found anywhere else. And finally, there is one article which is not very technical, but it tells you that it could be done. And with that, I conclude my talk, and I thank you for your attention. Next one. So just as a quick conclusion, Martin introduced during his introductory talk that we are organizing the European GNU Radio Days. So my frustration is that here we have 2 days of FOSDEM, we have 1 day full of talks, we never have time to discuss with each other, everyone's running to other sessions, and I wanted to have an opportunity to meet with people and sit together. So the way I organize this is 1 day of, or we organize this is 1 day of oral presentation, 1 day of tutorials. Everything is open at the moment. We are proposing some tutorial. Please feel free to propose new tutorials. Robin Getz is coming from Analog Devices to demonstrate the Pluto. So he told me, I hope, and I trust him. It is located in France, in Besançon. Besançon is a tiny remote city, which means that hotels are readily available. Here in the east of France, it's 2.5-hour train trip from Paris. It's a few hours from Karlsruhe. So I think it's a couple of hours from Karlsruhe. The call for contribution is March 21st. Registration is free, but please register because I need to organize. I need to know how many people are coming. So registration deadline is May 1st. The website is over here. And hopefully the evening dinner will be a barbecue so that everyone can talk to each other and have more time to discuss. So I will not waste your time with more advertisement, but please come.